Hey guys, it's Devin, and today we're going to be working through our first example problem. So this is going to be a dimensional analysis example, and this is the type of problem you can expect to find in your first week of your class. So the problem reads, 1 cubic meter of aluminum has a mass of 2.70 times 10 to the 3rd kilograms, and the same volume of iron has a mass of 7.80 times 10 to the 3rd kilograms. So it looks like what they're doing is they're trying to give us some information so that we can come up with density values for these metals. The problem goes on and it says, find the radius of a solid aluminum sphere that will balance a solid iron sphere of radius 2.00 centimeters on an equal arm balance. So the situation is that we have a scale, and the scale is going to be in balance, and on both arms of the scale we have two spheres. One side we have an aluminum sphere, and the other side that we have an iron sphere. And they want us to solve for the radius of this sphere that'll keep this scale in balance with this other sphere. Okay, great. Doesn't seem too bad. Prior to starting the problem though, a good practice is always listing out all the information that has been given to us that we can use to solve the problem, and then also trying to identify what it is that we're solving for. So they give us two metals, so let's go ahead and separate the information by metal. We're given information for the metal iron and also for aluminum. So for iron they give us a mass sample and a volume for that sample. So from there we can come up with a density value, and just recall that density, rho, is equal to the mass of the object divided by its volume. So we can say that the density of iron is going to be 7.80 kilograms. Oops. That is not right. It's going to be 7.80 times 10 to the 3 kilograms per cubic meter. They give us a radius for the iron sphere, so we can say that the radius for iron is going to be 2.00 centimeters. For aluminum, they give us a mass sample and a volume, so we can come up with a density value for aluminum. And that's going to be 2.70 times 10 to the 3rd kilograms per cubic meter. They don't give us any radius information. That's actually what we're trying to solve for. So this is going to be our variable of interest. So we'll just put a little question mark here for now. Also notice that with the information for the other quantities, we have that in kilograms and meters, but this radius that they gave us for iron is in centimeters. So it might be a good idea to try to convert that into meters. So let's go ahead and do that. So our conversion factor is going to be 1 centimeter per every 10 to the negative 2 meters. We can see that we can cancel out our units of centimeters, and we're going to have 2.00 times 10 to the negative 2 meters. Also, prior to actually solving the problem, sometimes it's great to look at the information they give us and try to reason out what our answer should look like. Sometimes we can come up with a prediction for our result, and after solving the problem, if our result agrees with our prediction, then we can feel pretty confident with our answer. So I'm going to give you guys two predictions. I'm going to say that the mass of aluminum should equal the mass of iron, and I'm also going to say that the radius of aluminum should be greater than the radius of iron. Now this right here is a little bit more obvious than this one, but let's go ahead and work out both of these and try to justify why these are going to be great predictions for this problem. So the scale's in balance, right? So that automatically makes me think that the weight of aluminum should equal the weight of iron. I guess we can assume that these are going to be weighed near the Earth's surface. So the weight is going to be given by the object's mass times our gravitational constant, which is going to be lowercase g. So we can say that the mass of aluminum times G is going to be equal to the mass of iron times G. And both these objects are going to be underneath the same influence of gravity. We see that it's on both sides of this equation, so we can just divide it out and it's gone. And there we have it. The mass of aluminum should be equal to the mass of iron. Okay, awesome. Now this one right here, assume that the radius of aluminum should be greater than the radius of iron. Let's consider their densities for a moment. We know that the density of iron was going to be 7.80 times 10 to the third kilograms per cubic meter, and that is going to be equal to the mass of iron divided by its volume. We also know that the density value for aluminum is going to be 2.70 times 10 to the third kilograms per cubic meter, and that's going to be equal to the mass of aluminum divided by the volume. So we know that the masses should be equal, but notice how these density values are different. In fact, aluminum's density value is much smaller than the density value of iron. Well, if the masses are equal, for this to work out, the volume of aluminum must be greater than the volume of iron. Let's go ahead and consider the volumes for a second. Now these are going to be spheres, so the volume of a sphere is going to be given by 4/3 pi times the radius cubed. So we can see that the cube of the radius is going to be directly proportional to the size of the volume. Well, if this volume is greater than that volume, then we can also assume that the radius of this aluminum sphere must be greater than the radius of this iron sphere. Okay, so let's go ahead and start trying to solve this problem, and let's just go ahead and try to confirm our predictions. So I think the best place to start is by having equal masses. So let's go ahead and equate the masses together. That was our first prediction, and I think that's a pretty solid assumption about the problem. So let's go ahead and say that we have the mass of aluminum, and that's going to be equal to the mass of iron. But we're trying to solve for the radius of the aluminum sphere. But we know that the radius is proportional to the volume, so maybe we can try to rewrite these mass quantities using volume information. And I'm thinking the best way to go about this is by using our definition of density. That was that the density, rho, was equal to the mass of the object divided by its volume. So we can solve this in terms of mass, and we'll get that the density times the volume is equal to the mass. So let's go to make this substitution in for our masses over here. So we can say that the density of aluminum times the volume of aluminum is going to be equal to the density of iron times the volume of iron. Well, we know something about the volume. We know that the volume is going to be 4/3 pi r cubed. So let's go ahead and substitute that value in. So we have density aluminum times 4/3 pi. The radius of aluminum we don't know, so we'll go ahead and just write it in like this, cubed. We're going to set that equal to the other side, so that's going to be the density of iron times the volume, which is going to be 4/3 pi. But we know this radius. This is going to be 2.00 times 10 to the negative 2 meters. We're going to cube that. Okay, looking at this equation, we see that we have common terms. We have 4/3 pi. We have 4/3 pi on this side as well. We can divide out that quantity and it'll cancel. So those are gone. That's always nice. Let's go ahead and apply this cube. So this value is going to turn into 8.00 times 10 to the negative 6 cubic meters. That's going to be multiplied by the density of iron. And on this side of the equation, we're left with the density of aluminum times the radius of aluminum cubed. So we want to solve for the radius of aluminum. Let's go ahead and isolate this by dividing out the density of aluminum. So we get that the cube of aluminum's radius is going to be equal to the density of iron divided by density of aluminum, and that's going to be multiplied by this quantity here, which is 8.00 times 10 to the negative 6 cubic meters. And let's go ahead and solve for the radius. So we're going to solve for the radius by taking the cube root of both sides. So we have the radius of aluminum is going to be equal to the cube root of density of iron divided by the density of aluminum times this quantity, 8.00 times 10 to the negative 6 meters cubed. Remember, that's all underneath this cube root. Before we actually substitute values in and actually solve for this, let's go ahead and consider the units here. Well, here we have a fraction. It's going to be a density units divided by density units. So the same units are going to cancel. It's like saying this. We have a kilogram over a cubic meter. That's all being divided by a kilogram over another cubic meter. We can see that these units are going to cancel. Over here we have a meter cubed, but we're taking the cube root of that, so what's going to be left over is going to be meters. We're solving for a radius, so our unit should be in terms of length, and that's what we have right here, so our units are great. So let's go ahead and substitute values in. So we have that the radius of aluminum is going to be equal to, well, the density of iron was going to be 7.80 times 10 to the third kilograms per cubic meter. That's going to be over 2.70 times 10 to the third kilograms per cubic meter. And multiplying by this quantity here, 8.00 times 10 to the negative 6 cubic meters. And again, that's all underneath this cube root. So again, our units cancel. We could also cancel off these 10 to the third powers. So we find that the radius of aluminum is going to equal 2.86 times 10 to the negative 2 meters. And let's go ahead and just go back to that prediction. So again, we were predicting that the radius of aluminum was going to be greater than the radius of iron. So this value right here was going to be 2.86 times 10 to the negative 2 meters. And the radius of iron was 2.00 times 10 to the negative 2 meters. And sure enough, this inequality holds. The radius of aluminum was greater than the radius of iron. So I hope that video was helpful. If you got something out of it, please subscribe to the channel and you'll be notified when new videos are available.